Good evening, everybody. Welcome to the Nobel panel on atomic physics. My name is Verònica Ahufinger. I'm professor at the Universitat Autònoma de Barcelona.
My name is Bruno Julia Díaz. I'm professor at the University of Barcelona.
We are both vice chairs of the 26th International Conference on Atomic Physics, ICAP 2018, which is taking place during this week here in Barcelona, gathering researchers from all over the world. The conference has been organized by 4 institutions: ICFO, Universitat de Barcelona, Universitat Autònoma de Barcelona, and Universitat Politècnica de Barcelona. One of the activities in the context of this conference is this open public event, which has been possible thanks to our sponsors.
Okay, after that, we would really like to thank you for coming to this event. And roughly, let's say, when the organization of this conference was being started, we thought that it would be very nice to have outreach activities to actually share, let's say, the joy of physics and of science with the general public. So it's really important for us, in particular all the people, of course everybody, but in particular all the people who are not from the conference. So thank you very much.
Unfortunately, we have to announce that one of our Nobel laureates that had to participate in this Nobel panel due to problems with the flight connection will not be able to be here today.
Well, just in case, what we wanted to break the ice a little bit, and we thought it would be fun to make a little estimate in the way that usually physicists do. So this is the typical physicist exercise.
How many stars are there in our galaxy? And how many grains of sand are there on the beach in Barcelona? How many Nobel laureates could there be in a gathering of 1,000 people like this one? Well, let's make a rough estimate. Considering that the total number of current worldwide Nobel laureates is around 300, and the number of adults in the world is approximately 5,000 million, the probability of finding one in a group of 1,000 people would be 300 times 1,000 divided by 5,000 million. That's more or less 0.000006. So what about finding 6? We would need to make the 6th power of that number, which is basically 0. Today seems to be the day where probabilities are defeated by atomic physicists. And we are very lucky to have among us 6 Nobel laureates to share with us their views on atomic physics and science in general.
Although, as I have said, we don't have 6 Nobel laureates, unfortunately in the panel we have 5 of them, that the probability to have also 5 Nobel Prize winners with us here is also very, very difficult. Let's welcome our panel that is formed, first of all, by Professor Claude Cohen-Tannoudji and Professor William Phillips, whose major contributions were to teach us how to cool and trap atoms with laser light. Welcome, Professor Cohen-Tannoudji. Welcome, Professor Bill Phillips. And thank you for being here today. We have also Professor Wolfgang Ketterle, who is one of the first persons in the world who was able to reach the lowest temperatures in the universe in his lab, producing the Bose-Einstein condensate. Welcome, Professor Ketterle.
And next, we have Professor Ted Hänsch, who actually received the Nobel Prize at the same year as Roy Glover in 2005, basically for finding ways to measure the atomic transitions with very high precision. So thank you for being here, Professor Hänsch. And our last member of the panel is Professor Serge Haroche, who actually managed to control quantum systems with really unprecedented precisions, all levels. So thank you very much for coming here, Professor Haroche.
After this brief introduction, let us start with the session on the past, present, and future on atomic physics. The session will be formed by, or consist in 3 parts. In each part, we will start by showing a short video that will introduce a question to our panel in order to motivate the discussion. So let's start with the first of them.
What's our universe made of? In their search for the truth, atomic physicists look at the fundamental blocks of matter and light, which are atoms and photons. They seek to understand the individual properties of atoms, but also how atoms interact one with another, or how they behave when they're shined by light. An atom has a very small size, on the order of 10 to the minus 10 meters. And at such scales, nature is ruled by the laws of quantum physics, which are full of unexpected surprises. Since the early days of quantum mechanics, atomic physics has made giant steps to enlighten the quantum behavior of matter and light. Along this journey, the use of lasers has been fundamental to see how atoms and molecules are and behave.
Okay, so let's just to frame a little bit the first question that we wanted to pose to the panel. So basically, understanding the structure of the atom required developing one of the most striking and successful theories, right, which is quantum mechanics. So in a sense, we would like to ask you, I mean, what is, first of all, maybe the aspect of quantum mechanics that you like best? And also, in a sense, how has atomic physics helped us to learn about quantum mechanics and maybe even about nature itself? So how has atomic physics, what has atomic physics taught us about nature in a very general frame? And maybe we could start with Professor Cohen-Tannoudji, if you want to break the ice, so to say.
Okay. I think that atomic physics has played a very important and essential role in the spreading of quantum mechanical ideas. I remember when I started to do research about 60 years ago, quantum mechanics was even not taught at university. It was considered as a theory just explaining the spectrum of atomic hydrogen. Now quantum mechanics is everywhere in our world. All people know a lot of applications, lasers, transistors. Everything in our world now is based on quantum mechanics, and quantum ideas. And I think one of the main achievements of atomic physics is to have performed simple experiment demonstrating the properties of quantum states. Mm-hmm. 2 of them are particularly important. Quantum states are linearly superposed. If you have 2 states, psi1 and psi2, there exists also states which are a linear combination of these 2 states, C1 psi1 plus C2 psi2. And in such a superposition, the system is not in psi1 or in psi2, it is in the same time in psi1 and psi2. Mm-hmm. And for example, if psi1 and psi2 are 2 states with different positions, that means that the system can be 2 different places at the same time, which is very difficult to imagine, but which is true in the microscopic level. Another important property of quantum state that you can consider also linear superposition of combined state of 2 systems, so-called entangled states. For example, if you have 2 spins, you can have a superposition of spin 1 plus and spin 2 down, and spin 1 down and spin 2 up. That's also very strange, because if the 2 systems are very far apart, if you measure spin 1 in the spin up, you are sure that if an observer observes spin 2, it will find it in down. So you have some sort of transmission, instantaneous transmission of information. Of course, general relativity is not violated, but these states are not local and non-separable. And what is important now is that these entangled states are very promising for quantum information, for transmitting information very far away, for treating information in a very compact and rapid way. So this is very promising. To sum up, I would like to say that really quantum mechanics has played a very important role in improving the perception of quantum features in the society, in all layers of the society, not only in the general public, but also in universities, in industrial companies. That was not the case a few decades ago. And atomic physics has contributed to this better perception in a very important way, and I think we can be proud of it.
Let me just mention, because most of you, well, some of you maybe don't know that a lot of people have learned quantum mechanics following the books of Professor Cohen-Tannoudji. So in a sense, it's quite interesting per se to know what you find is more striking in quantum mechanics. For instance, you find more striking, let's say, superpositions than quantization itself, I guess, no? And you all share this view. I mean, in a sense, we would like to, is this something that, or there are other aspects of quantum mechanics related to atomic physics that you find more striking?
Well, I would have said exactly the same thing. In fact, when you asked the question, what are your favorite aspects of quantum mechanics, I immediately thought superposition and entanglement. And then that's exactly what Claude said. So I think that at least we share that. Let me just say a little bit more about that and why I find that so fascinating. Claude made the very good point that while in ordinary life we often say, well, you can't be in two places at the same time, in the atomic world you can, and in fact we do that sort of thing routinely in the laboratory. That is, we arrange for a situation where an atom can be here and also here at the same time. Now the thing that's interesting is, if you measure where the atom is, you will get one or the other of those two answers. And our usual understanding of the nature of reality is that if we measure a property of something, that property, for example, that it's on the left or that it's on the right, that property is something that exists before we measure it. But if we were to assume that a property like that existed before we measured it, we would be wrong. And we can do experiments to show that we would be wrong to assume that the property existed before we measured it. That changes our very notion of what constitutes physical reality. The fact that things, the properties of things, don't really exist until we measure them is something that goes against our usual understanding of the way the world works. And it was so strange that Einstein felt that quantum mechanics could not be correct. He understood better than most people what quantum mechanics implied and felt it could not be correct because it was so strange. But in fact, all the experiments that have been done show that quantum mechanics is exactly that strange.
And that experiment were atomic physics experiments.
Yes.
That's important. That atomic physics proved that this situation is what exists in the world.
And Professor Ketterle, do you agree with his view?
Well, of course, I Bill. But let me kind of give you my thoughts from a different angle. When I teach undergraduate and graduate students and introduce them into the wonderful world of quantum mechanics, it really means an exciting journey because you teach people about the world. You teach people how the world works. And I often have students who have taken already classes in quantum mechanics. But quantum mechanics is something you can read about it, you can solve problems, you can solve equations, and you can understand it. And I often see that even rather experienced students do not have the full intuition for quantum mechanics. And I create with them the intuition by using examples from atomic physics. Atomic physics is the place where I've seen where students really learn, and not just learn, but understand the quantum mechanics. Because you can ask about so many situations. What would happen with atoms here? What would happen when you do a measurement? What happens when you do two measurements in series? But in atomic physics, we have done it experimentally, so it's real. And you can always connect the learning process with connections to real experiments, which in a very impressive way demonstrate what quantum mechanics really is about. So for me, atomic physics is kind of often the first example where you can directly apply the formalism of quantum mechanics and without any extra complexity understand the foundational things. And this is what I kind of enjoy in the classroom, to see how students first get very confused, but then they get very excited because it's an intellectual pleasure to understand it and suddenly have paradoxes, seemingly paradoxes with our normal understanding and see how they are dissolved, how they disappear.
And if we now reshape maybe the question, so which are the key discoveries that you think, maybe Professor Hänsch, that have led the progress of physics, so atomic and molecular and optical physics, during the history in the past?
The recent, in the old years, you mean? No?
Professor Haroche, maybe you can. Yeah, okay. Yeah.
Okay. So, well, I mean, it's no question that atomic physics is at the heart of all science. Anything that we can see or touch or smell is made of atoms. And to understand how these atoms work, of course, is a fantastic science. I do not agree that we truly understand quantum mechanics. We understand the formalism. We can predict the probability of getting a certain outcome in an experiment. But what it means, I don't understand. Nonetheless, I mean, these counterintuitive, strange laws of quantum physics have been discovered by people who investigated the simplest of the atoms, the hydrogen atom. And they are from the old quantum physics of Bohr to wave mechanics, to relativistic quantum mechanics, to radiative corrections and quantum field theories, quantum electrodynamics. Almost all new insights came from looking at the spectrum of the simplest of the atoms and from realizing that there are small discrepancies between theory and experiment. And so I think this is a line that might lead us to future fundamental insights, but it's a beautiful area of physics, and it has created insights into a world that we cannot grasp with our intuition. And people are still wondering, what do we really describe, say, by a wave function? Is a wave function something real that can collapse? Is it something in our mind? So there are still many open questions.
Actually, being experts, let's say, in atomic physics, have you developed this kind of intuition, quantum intuition? I mean, we live in a classical world. So developing intuition in quantum is not so easy. I mean, I guess once you have been working with these tools in atomic physics for a long time, right, you start having some sort of intuitive behavior, no? So is this something, for instance, that you, when you are doing your research, you have to switch, let's say, from your classical intuition to the quantum intuition? Or?
Yeah. I would like to touch this question under another perspective. It has been said that one of the fascinating features of quantum physics is that the system can be in different states at the same time. Mm-hmm. And when you perform a measurement, the system has to decide, but this decision is made when the measurement is made, and there was no reality to the result before the experiment was made. And another important feature is that the result of the experiment is random. You cannot know, and nothing in the theory can tell you which result you will find if you make the measurement on a system which was prepared in a superposition of states. And this randomness is also a feature which is very strange and very difficult to understand for physicists, because until quantum physics started, one of the major assumptions of physics is that once you have prepared the system, once the initial conditions are known, everything should follow according to the equations. This was the case of Newton physics, and the big triumphs of Newton physics was that you could explain the motion of the planets and all the mechanics according to this rule. And the fact that quantum physics has to abandon this idea of determinism, what is called determinism, was one of the features which made Einstein very reluctant to accept this as the ultimate truth. And this is paradoxical because the idea that physics is not deterministic led, for instance, to the Heisenberg uncertainty relations that everybody knows about, even if it has not done any physics. The fact that you cannot measure with absolute precision at the same time the position and the velocity of a particle. And this seems to indicate that the quantum physics is fuzzy, that quantum physics has at its core some kind of fuzziness which makes measurement not very precise. But in fact, it is quite the opposite. If you use quantum physics and the laws of quantum physics, you can make measurements which are much more precise than the one you could make if the world was obeying classical physics. I will just take one example. A classical clock is based on the motion of the periodic motion of a classical system, and it has an uncertainty because you cannot make two clocks identical. Mm-hmm. On the other hand, if you apply the laws of quantum physics and if you rely on the motion of electrons in atoms, you can make clocks which by definition have the same ticking rate, and you can make measurements which are exceedingly precise in a way which is very hard to imagine. You have now atomic clocks which can keep time with a precision of the order of better than 1 second in the age of the universe. And all this is based on the laws of quantum physics. So quantum physics is not fuzzy in spite of the fact that it has some randomness in it. And I think this is a paradox which is very deep and which is very hard to really understand because it's counterintuitive, I would say.
Okay, thank you very much for your views on the past of atomic, molecular, and optical physics. And now that we have learned a bit, very briefly, but the time goes on, so about quantum mechanics and the beauty of quantum mechanics, maybe it's time to move to the present, and we will do it showing our second video.
Oh.
In the last 30 years, an unprecedented level of precision in preparing, manipulating, and detecting atoms in light, as well as controlling their interactions, has been achieved, opening new avenues to an astonishing control of nature. Techniques to cool down atoms to the lowest temperatures in the universe are of current use nowadays in many labs worldwide and allow entering a new realm of nature where, for instance, new forms of matter are possible. Thanks to impressive technological advances, atomic physicists are now able to address single atoms and single photons at the quantum level. Not only can they manipulate, but they can also measure with groundbreaking accuracy. The most precise atomic clock could measure the estimated lifetime of the universe with an error of less than 100 milliseconds.
Okay, so let's say, well, in this part of the discussion, what we would want it to go is a little bit closer to the present, let's say. So previously, we were discussing a little bit of the foundations or the early achievements of the field. And here we wanted to go a little bit closer to your own achievements, let's say, which have allowed us to control matter and light with unprecedented precision, right?
Yes, indeed. Controlling and manipulating atoms and light at the lowest scales, I guess you would agree that is one of the main achievements of our community. And also, in fact, most of the achievements, the fast and impressive achievements of atomic and molecular and optical physics during the last years are based on the works of this panel. So we would like to take the advantage of having you here to show or to know from the main actors which is your personal view and experience on manipulating atoms, light, molecules at the lowest scales. So maybe, please, Professor Haroche, would you like to start?
Yes, okay. This field of physics has started about 25 or 30 years ago. Up to that time, the experiments on atoms were made on big ensembles of atoms because we didn't have the sensitivity which was high enough to be able to see individual particles. And this was something which was very surprising. The fact that we could measure single particles and manipulate them is something which was very surprising to the founding fathers of quantum physics. For instance, Schrödinger was one of the very important people at the beginning of quantum physics, the one who found out the Schrödinger's equation, on which all quantum physics is based, did not believe that it would be possible to manipulate single quantum system. He said, we imagine that we are doing that in thought experiments, but if we really try to figure out what would happen, then very strange and ridiculous things would happen. So the reason why the physicists have started to do that, first because technology has evolved, that lasers became so precise that they were able to manipulate particles at this level. And second, because it was a challenge. It was very important to find out whether it was possible and possibly to prove Schrödinger wrong. I want to say that the lasers themselves, which were used to do that, are results of which were obtained from quantum physics, from theoretical ideas about quantum physics. So all this is an illustration of a kind of virtuous circle, the fact that the theory allows to develop instruments which in turn allow us to improve the precision of experiments and maybe to check if the theory is correct. And many examples of that have come up in the last years. So about 25 or 30 years ago, it has become possible to observe a single atom and to see really, almost with naked eyes, the quantum jumps, what happens when an atom is going from one quantum state to another one, which is something that, for example, Schrödinger never believed would be possible, and he always questioned the notion of quantum jumps. So this has become possible out of fundamental research. It was not done because we thought that it would be interesting for applications, but as soon as it has happened, as soon as it has become possible to manipulate and to control single quantum particles, people have started to have the idea that this could be useful maybe one day for something. For example, for making better communication, for making more precise measurements, or maybe one day for computing in a way which is not possible according to classical logic. So what I want to say is that all this illustrates what research is about, not only research in atomic physics or in quantum physics, but research in general, which is, at the start, has to be motivated by curiosity. And then, when the basis for research have been laid out clearly, then the application can come, and then people can start to discuss the possibility to use that for the present or for the future. It's very hard, as you know, to predict what will happen in the future, but what is clear is that without this basic science at the start, nothing would happen anyway. So it's very important to have this in mind.
Professor Cohen-Tannoudji, maybe.
You know, I think during the last few decades, the progress in our ability to manipulate and to control atoms and light is really impressive. But I think that a few general ideas can explain why it happened. First, conservation laws. The first example is conservation of angular momentum. Polarized photons carry angular momentum. And when atoms absorb polarized photons, they become polarized. And that was the very simple idea that Alfred Kastler developed in the 1950s, and which is called optical pumping, of polarizing atoms with light. And I would like to emphasize that these experiments were performed before lasers with classical sources. Another conservation law, which is very important, is conservation of linear momentum. You know, when you have a laser beam, for example, all photons have the same direction and the same momentum. And when atoms absorb these photons, they gain the linear momentum of these photons. And as a result, they feel a radiation pressure which changes their velocity. And that's the principal idea of stopping an atomic beam and then after that cooling it and trapping it. Another important general idea is that atoms perturb light and light perturbs atoms. When you have a light beam propagating through an atomic medium, it can be absorbed and the velocity of propagation can be changed. That's described by the index of refraction having a real part and an imaginary part. And the symmetrical effect exists for atoms. When atoms are put in a light beam, their levels are broadened because they get a finite lifetime due to the real absorption and remission of photons. And they are also shifted because of virtual absorption and remission of photons. So you have two similar effects at the real and imaginary part of the index of refraction. And you know, this light shift can be considered as a radiative correction, similar to the well-known lamp shift, which is due to virtual emission and reabsorption of photons, and what's the starting point of QED. And Alfred Kastler, with his sense of humor, was calling light shift the lamp shift, because they were looking lamp shift, except that instead of the vacuum field, you have the field coming from a lamp. And what is amusing is that effects studied in the 1950s turn out, a few decades after, to be useful in the new field of laser cooling and trapping. For example, light shift, if the beam is detuned far from resonance, you have no real absorption, and the broadening of the levels is negligible. And the light shift appears as a non-dissipative potential, which can trap atoms. And one famous example of that, you can trap now atoms in a periodic array of potential wells produced by a laser standing wave. And you have what is called an optical lattice, and which is some sort similar to an electron gas in a solid. And these optical lattices appear now to be a very important model for better understanding of solid-state physics. If the light beam is not detuned too far from resonance, then you have both real and virtual absorption of photons, and you have both mixture of light shift and optical pumping. And that has given rise to a new laser cooling scheme where the atoms climb the potential hill produced by the light shift, and when it is at the top of the hill, it can make an optical pumping cycle to another state which is at the bottom of a valley, and so on and so on. So it's like the situation of the hero of the Greek mythology, Sisyphus, who was condemned to climb potential hill. And when he was at the top of the hill, he was put down. Yeah. And you know, that allowed laser cooling to reach the microkelvin range, about 100 times slower than Doppler cooling. And that was really the starting point of laser cooling. A few years later, another effect, which was well known in atomic physics, the dark states. You have states which are linear combination, linear superposition of two ground state sublevels, such that the two absorption amplitudes to a common excited state interfere destructively. Such a state cannot absorb light, and it is protected from the random recoil due to spontaneous emission. Now, how you can cool atoms if you have no spontaneous emission? But atoms which are not in the dark state, because you can make the dark state velocity dependent, can by fall very near v equals 0 corresponding to the dark state. And you can accumulate atoms around this value V equals 0 and get a limit of the cooling which is 0. You can cool atoms as well as you want.
But maybe as we
Of
have
course,
here,
it's not easy.
Yeah, maybe that we are talking about cooling. So why is so important, maybe Professor Ketterle, why is so important to reach these lowest temperatures that you reach in the lab using maybe also
okay. Let me answer this question in 30 seconds, but first point out that you will usually see all of us agree. But there should also be maybe some disagreement, and I would say I disagree with some people who say they don't understand quantum mechanics. I think I can even feel the wave function of atoms if I do research or we look at data we've taken in the lab. So for me, quantum mechanics has no mysteries. It's fully understood. There may be some people who have a philosophical uneasiness with the randomness of quantum mechanics, but well, I'm happy to simply accept that as a piece of, that's how nature works. If you really hard press me, I have some trouble explaining what the wave function of the universe is, because there's no observer who would measure this wave function. But except for that, I usually say I fully understand quantum mechanics. But anyway, this was just a comment about the previous round. Okay. Now, why is it important to cool atoms down to low temperature? Let me maybe put it in the context which, for me, it was the experience of a lifetime to see how atomic physics profoundly changed. For so many decades, atomic physics was about atomic structure, understanding atoms, understanding the spectrum of light, or understanding how light is absorbed and emitted. But what happened, because we reached very low temperature, is that atoms became so slow that they started intimately feeling out each other, and atomic physics was transformed from the physics of one atom, or maybe two atoms when they form a molecule and collide, to many-body physics. To suddenly have atomic physics being able to address the question, what happens when thousands and millions of atoms interact? This has been a revolutionary transformation, because it means the methods and the concept of atomic physics are now applied to the behavior of many atoms, and this is material science at the fundamental level. So for me, it was the experience of a lifetime to see this change, but the enabling technology, or one of the enabling technology, was very low temperature.
Bill Phillips, you are one of the persons who stopped atoms, let's say, with laser light. And the kind of joy that you get from this kind of control is, I mean, what is driving you, so to say?
Well, actually, I'm glad you asked that question, because it gives me an opportunity to comment on something that Serge said. Serge said that one of the important things about the progress of science was that people were following their curiosity, that it was our curiosity about nature that leads to progress. And that's what has always driven me, is a curiosity about how things work and how we can understand better how things work. But this is the point I want to make. Oftentimes, young people especially, and I think there's some young people in the audience, although they've turned the lights out so that it's hard for us to see.
There are many. Yeah.
Ask, what is the most important thing if you want to be a scientist? What should you do? And the answer that I give is stay curious. That I believe that is the most important quality of a scientist. Of course, there's many important things. You should study. You agree, but I'm going to disagree with you in just a moment. but there are many other things you should do. Of course, you should study math and science. You should also study language, because communication is so important in science. But I really think the most important thing is to stay curious. And one of the things that I love about really young children is they're curious about everything. And I often tell groups of young children when I talk to them that I like talking to them most because they are the most like scientists. Because scientists are simply little children who have never grown out of that natural curiosity. Now let me disagree with Wolfgang about understanding quantum mechanics. Now, of course he's right. there's nothing in the quantum world that we can't calculate, that we don't know how to calculate. There are some things that are just too difficult for us to calculate, but there's nothing that we don't understand how to calculate the results. But yet, at the same time, we don't understand how it happens that something can go from being in two places at the same time, according to its wave function, to end up being in one of those two places, and how does it choose? We don't understand that. Now, we don't need to understand that in order to do the science that we do. And as an experimentalist, I strongly ascribe to the school of interpretation of quantum mechanics known as shut up and calculate. And the idea here is stop thinking about all these difficult problems and just do what you've been taught to do, and you'll get the right answer if you do it right. The trouble is that, you know, sometimes when you can't sleep at night, you think, but wait a minute, I don't really understand this. And so I'm open to thinking about these, what some people call the foundations of quantum mechanics, the fundamental problems of quantum mechanics. And it might be that by thinking about it enough, we'll find out that there's actually something more than quantum mechanics, that there is something that we could learn that would be different. And if we ignore these uncomfortable aspects of quantum mechanics, we may miss something important. And so, essentially, I'm a quantum mechanical superposition of understanding quantum mechanics and not understanding it.
I think Professor Haroche may agree or disagree, I don't know.
I think that all this discussion comes back to the origin of quantum physics, and we should talk about Einstein, because he had all these ideas in his work. The fact that quantum effects appear at low temperatures is something that he has understood even much before quantum physics was put into its modern form. For instance, in 1911, at the Solvay meeting where the quantum ideas were discussed for the first time, Einstein presented a paper on the heat capacity of metals, and he described the fact that at very low temperature, the heat capacity of metals goes to zero because the motion of the atoms are frozen, and this freezing is also essential to understand why the Planck's law for radiation is valid, and all comes back to the fact that quantum phenomena appear at very low temperature. So Einstein had understood that, and he has also understood that if you could bring atoms to very, very low temperatures, then they would condensate into what is called the Bose-Einstein condensation, which was observed for the first time 70 years later, especially by Wolfgang in 1995 experiment. So the fact that quantum physics works at low temperature and that the quantum effects are manifest at low temperature is a very important feature. Superconductivity, the fact that metals are carrying currents without any losses, is also a feature which occurs at low temperature or very low temperatures, and this is also a quantum phenomenon. So this is a very important and basic idea. Now, whether you understand or not really what's going on at the philosophical level is another question. And I must say that you get some intuition, even when you do experiments, when you put a system under very well-defined conditions, you have an intuition of what will happen, even if it is not the common intuition of everyday life. So intuition is based on evolution. It's clear that our brains are used to understand what happens at the macroscopic scale because it's helpful. If you are thrown a stone at, it's important to realize what the trajectory of the stone will be to avoid it. And we have never been confronted with stones going from two different sides at the same time, just one stone following different trajectories, so we did not build this kind of intuition. So maybe after many, many generations, if you still have young people who want to go into physics, maybe in many generations this intuition will be in our brains and we will not have this question anymore to ask. But this is something which will take a lot of time, obviously.
I think Professor Cohen-Tannoudji wants to add something.
I think we all agree that we know exactly how to do a quantum mechanical calculation and how to interpret a given experiment, and it's always successful. But I don't agree with you, Wolfgang, when you say there is no problem. There are still problems. You know, when you teach quantum mechanics, you introduce several postulates. One is the evolution in time, which is described by Schrödinger equation. And what is the measurement? When you make a measurement, you postulate that the system makes a quantum jump into the eigenstate corresponding to the measurement you have done. So you have a difference between a reversible oscillation between two measurements and the quantum jump during the measurement. That cannot, you feel uncomfortable with these two types of evolution. Can we include the measurement process in a current way with the evolution in time? Of course, people try to involve the measuring apparatus and to treat it quantum mechanically. But you still do move the problem further and further, because at some time you must have a quantum measurement and a quantum jump. I think that the problem which is considered here is the border between quantum physics and classical physics. I think that probably would reveal new ideas when this border is investigated with more carefully. A second problem, which you cannot avoid, is that actually, presently, quantum mechanics is not compatible with general relativity. That's a little uncomfortable. So what I hope is that with the extreme high precision that we reach now with the development in atomic physics, one could make tests of general relativity, tests of gravitation, which perhaps could help solving this problem. So, of course, quantum mechanics is wonderful. I am a very fan of quantum mechanics. I wrote several books on quantum mechanics. I like it. But it's not completely, I'm sure it's not the full theory. And probably young people in a few years will find important progress and a better understanding of the mysterious aspect of quantum mechanics.
I'm sorry, but yeah. Oh,
yes,
please.
Since I started this discussion, I would certainly hope that quantum mechanics, as we know it today, is not the end of insights. I'm very sure there are deeper theories yet to be discovered that tell us why quantum mechanics behaves in the way we know. Nonetheless, I mean, quantum mechanics is extremely successful, and to find a dent in this framework, maybe making more precise measurements is one way. And that is something that has kept me going for a long time. Even as a graduate student, I realized that with lasers, you could do spectroscopy with much higher resolution and higher precision than was possible with classical instruments. Then I was lucky to come up with an idea to make narrowband tunable lasers that opened up a huge range of possibilities in atomic spectroscopy and molecular spectroscopy. We focused on the simple hydrogen atom in the hope that if we improve precision and resolution, that we find a dent in this framework of quantum physics. So far, we have not found it, at least we are not sure. But this quest for ever higher resolution, higher accuracy, has motivated inventions that have proven very fruitful. The proposal by Archolo and myself that you could cool atomic gases with laser light, of course, has led to fantastic achievements. The frequency comb technique that we use now to measure the frequency of light makes it possible to design optical atomic clocks that in the future might give you gravitational effects on a scale of sub-millimeter. If we want to combine general relativity and quantum physics, maybe there is an approach to do that. But I think we have to be aware of the limits of our present knowledge.
Well, actually, because we are starting to talk about future, let's say this was our last part. So if it's okay, let's move to the next part, which basically is about the future. So let's take a look at the last video.
The world is changing in very unpredictable ways. With new techniques developed in atomic physics laboratories worldwide, we will be able to engineer new materials built by controlling single atoms and photons with unprecedented precision. Human-tailored magnetic materials, superfluids, and superconductors will bring quantum technologies to our everyday life. Entanglement, one of the mysterious properties of quantum mechanics, will become a valuable resource to exponentially improve our ability to measure the basic constants of nature, perform large calculations, handle information, and encrypt our communications. Atomic physics will be at the forefront of this quantum revolution.
So we know that predicting is always tricky. But at this last part, we would like to invite you to speculate a bit on what do you think are the most promising or the most exciting venues of atomic physics right now. And in particular, we would like to know also your opinion about the predicted second quantum revolution. So would you convey, for instance, that this predicted second quantum revolution will reshape the way the world is and will affect our everyday lives? So maybe Professor Phillips, could you like to start?
Well, I'd like to begin by defining what this means for everybody, because I think I may be guilty of promoting this idea of a second quantum revolution, so I should have the punishment of having to explain what I mean. The first quantum revolution was the one that happened in the 20th century. And while that development of quantum mechanics gave us ideas like superposition and entanglement, the fact is that those ideas, the ones that we love so dearly, the ones that we find so mysterious, those ideas were not put into practical use in almost all of the applications of quantum mechanics. Quantum mechanics has given us most of the things that we associate with modern technological society. Our cell phones, our computers, our televisions, our global positioning network for navigation, even my watch is quantum mechanical. I used to have a mechanical one, but it didn't work nearly as well as a quantum mechanical one. And so, but all of these things were given to us by really quite simple ideas of 20th century quantum mechanics, the idea that particles like electrons behave like waves. Now, in the 20th century, we are, I believe, on the threshold of a second quantum revolution where the ideas of superposition and entanglement will be central to new kinds of technology. And it's hard to believe that that second quantum revolution is going to be as profound as the first one, because the first one changed our lives in unimaginable ways. But it's also dangerous to ever say that something is not going to develop to be important. In the 1980s, the presidents of major computer companies said, no one will ever need a computer in their home. And of course, those companies don't exist anymore, and everyone has 100 computers in their home. So if I were to predict that the second quantum revolution will lead to devices that will be used by a few people in advanced laboratories, I could be incredibly wrong to make that kind of a prediction. So I think I'll leave my comments about the second quantum revolution there, having described a little bit about what it means, and let others say what they think will come of it.
Sure. Which is your opinion, for instance, Professor Ketterle?
Of course, I agree with what Bill has said. I just want to make a historical remark. I don't think any physicist back in the 1920s has ever said that they were doing the first quantum revolution. They just did it without talking about it. Of course. And what I don't like is that we talk too much about this quantum revolution without knowing what it will lead to. It's clear that it's already there for applications which are useful for physicists to work in the lab. It's obvious that we have now better ways to probe things, to make very precise measurements. The clock, the example given by Ted about the fantastic precision of optical atomic clocks is one example of what this quantum revolution is about. But of course, these are applications which are not going to be in everyone's home, as Bill has said. And whether you will have applications which will change the everyday life using quantum logic is something which may happen or may not happen. We don't know about it. And I don't like the idea that we have to promote it all the time just to get funding, because we need money to do experiments, and so people have a tendency to oversell things. I think we just work out of curiosity. We try to do things practically, but we don't know where it will exactly lead to. Everyone is talking about the quantum computer, a computer which will be much more powerful and will be able to do computations that the classical computer cannot do. Whether this will happen or not, I think nobody knows. Some people have reservations about whether it will work or not. But today we already have what we call quantum simulators. The fact that we can put atoms on a regular array on a lattice and simulate what would happen in ordinary matter and learn a lot of things about what happens in condensed matter physics using this. This is something which already exists in the lab. It's not something which will be developed for everybody to have at home, but it's very important, I think. And this is, again, what I think we should do. We should try to do as best as we can in research without knowing what the application will be in the future. If you take examples from the past, this is what happened in the 20th century. For example, the people who invented nuclear magnetic resonance, Felix Bloch and Edward Purcell, back in 1945, did not know what it would be useful for. And I think they were still alive when this was developed into the IRM, the magnetic resonance imaging, which is so powerful in medicine now as a way to make images of the inside of our bodies. And they were really, Edward Purcell was really amazed by the development of his own research back in the 1940s. So I agree with Bill that maybe in 30 or 40 years from now, there will be fantastic things using quantum logic, but I guess that this will not be what we figure out today.
And why is atomic physics playing a role here somehow? I mean, for the general audience, in a sense.
For example, quantum simulators are based on atomic physics. You play with atoms on a chessboard, kind of chessboard, and find new rules obeyed by these systems. And atomic clocks are doing the same, are also working in atomic physics. Another last example I have in mind is the discovery of gravitational waves, which was done 2 years ago. And this was possible because of development of very powerful lasers whose phase can be controlled with an extreme precision. So it's not really atomic physics, but it's what is called AMO physics, atomic, molecular, and optical physics. And this opens new windows to the universe. Gravitational wave detectors are giving us information that no optical telescope or microwave telescope can give us about the universe. And this is again something which comes from the community of atomic physicists.
I think atomic physics can play a major role in the further development of quantum mechanics and applications of quantum mechanics, because atoms have just the right size. I mean, if you take subatomic particles or nuclei, their energy scales are so large that you cannot easily manipulate them, whereas we can manipulate and control atoms with lasers. If you go to bigger objects, to macroscopic objects or solid-state devices, they usually decohere so fast because they're more complex. So in that sense, the atoms are just in the middle, have just the right size. They say we can isolate them sufficiently well, but we can still manipulate them. And this is why a lot of developments in applying quantum mechanics, quantum simulators and such, comes from atomic physics. Maybe let me make a comment about the quantum revolution. I like to take the letter R out and call it evolution, because I feel in the last 20 years we had an exciting times which continues, and I don't see the step function which would be indicative for revolution, like a big step. I just see many, many steps which have given us the ability to control single quantum states, single atoms, and single photons. And also, if I look back just at current research or recent accomplishments, the concepts of topological physics, topological insulators, the fact that materials are not fully characterized by energy and momentum, by band structure. There are other topological invariants which can profoundly change the behavior of materials. This has been, for me, major insight, but this major insight is single particle quantum physics, non-interacting particles, the band structure of non-interacting particles. This is what has topological properties. And it's probably difficult, Bill, to include single particle physics into the second quantum revolution. So I'm just saying quantum physics is exciting, and to label it or to make entanglement and superposition principle as the future is maybe too narrow. I see a lot of excitement for quantum physics, but maybe not in a revolutionary, more in an evolutionary way.
I think there is presently a trend which is very important in the field of atomic physics, is what people call quantum simulation. They try to make a system of atoms which simulate more complex systems, which could, without any hope to be calculated. These quantum simulation systems can provide new ideas and new results. And I am wondering if quantum simulation could help to simulate biological systems or living organisms. That would be a real revolution if quantum ideas penetrate biology. And it's so complicated that I think the only way to get into is to make quantum simulation, to make system. You know, during the meeting, we have seen very complex systems which look like living organisms, some chain networks. That, I think, could be very exciting if some simple ideas emerge from simulation of complex organisms, similar to living organisms. That would be a real revolution. But it's not the case presently. But if we hope, if we are predicting the future, that could be a very important issue.
But actually, during the conference, let's say, we have been seeing that a lot of people are producing new materials. So in a sense, this is also what we meant, in a sense, by revolution, in the sense that new materials are produced that may have properties, as Professor Ketterle was saying, like topological, right, that connect with fields of mathematics that were not so connected before. So in a sense, this
people
is
speak of neural networks, you know. Understanding the functioning of the brain would be fantastic by simulating with chain of atoms coupled together. That would be a real revolution.
Sure.
Yeah.
But perhaps I'm too optimistic. Perhaps it will take a very long time before reaching this level.
I think you're very optimistic
But you
here.
are dreaming.
Yes.
You can
A bit pessimistic there.
Yes. Which is your opinion, for instance, Professor Hänsch?
Regarding the second revolution, I think I share the opinion of Serge Haroche, and I hope that there will be much more fantastic revolutions coming due to new, unexpected insights. In the 80s, Dan Kleppner, who is here, was chairman of a committee of the US National Academy of Sciences tasked with predicting the future of atomic, optical, and molecular physics for the next decade. And there were many predictions. One thing that made it was a prediction that we would have hydrodynamic computers working with liquids and fine channels, and had many advantages. There would be no danger of sparks, so they could work in explosive atmospheres and so forth. But what we did not predict was Eric Cornell and Carl Wyman's first demonstration of Bose-Einstein condensation of cold alkali atoms and all the things that evolved from there. So I think there will be, maybe next year, maybe in 3 years, there will be new insights, new discoveries that will change the direction of the field. And I am not able to predict.
Yeah, but in a sense, let's say, what would be, Bill, the most dream thing that you would like to see from atomic physics, in a sense? If you have any, I mean, there is no need.
Well, of course we have dreams, but Ted is absolutely right. We're very bad at predicting. I remember when I was a boy, they predicted that by now we would all have our own private rocket ships, and we would commute to work in some sort of a rocket, and no one predicted that we would have computers. Even though all of the science that was needed to understand how to make computers already existed when I was a boy, nobody imagined that the future would be dominated by computers. So we're really bad at predicting things. But what I would like to see, I would like to see really great quantum computers that could solve difficult quantum mechanical problems. We've talked about how we know how to do quantum calculations, and we do, but sometimes, even though we know how to do them, it's so hard to do all the steps because there are so many steps that we can't do them even though we know how. And a quantum computer could do many of those calculations and give us insights into new materials that we have a great deal of difficulty getting now simply because we can't do the calculations. So I would love to see competent quantum computers built. I would love to see a resolution of the problem of how to reconcile quantum mechanics with gravity. And I would love it if atomic physics were the route that showed us the path by, for example, finding a violation of Einstein's principle of equivalence. For example, if two different atomic clocks kept different time as you changed them in a gravitational field, that would give us a clue that this was the weak point of gravity and might give us an insight into how to change general relativity to make it compatible with quantum mechanics. That would be wonderful. Whether any of these things will come to pass, I don't know. I ascribe to the philosophy of that great American philosopher, Yogi Berra, who was a catcher for the New York Yankees baseball team. And what Yogi Berra said was, prediction is difficult, especially about the future.
Yes.
Sure. No, but actually I find it funny that even you are dreaming about a new quantum computer, for instance, but you want to use it to do research.
Yes.
You don't want to use it to decipher things or break communications, but simply to learn more, right?
Yeah, you know, deciphering things, that's what produces a lot of money for these things. But now we have a number of people working on quantum-resistant encryption algorithms, so probably that's not going to be the important application of quantum computers. But doing quantum mechanics, that's a natural application of quantum computers, and there's so much important quantum mechanics to be done.
Yes, maybe one of the take-home messages is, because it has appeared many times, that the fundamental research is something that we have to pursue, and this is really what it's driven, the technological applications that will come in the future. But we have to enjoy doing physics and doing fundamental research.
Any of you want to add something?
Yeah, maybe we talked about things that we don't understand, and the fact that quantum physics and general relativity are not compatible is one point. Cosmologists are telling us that we don't know 95% of the universe, that there is some what is called dark matter, which does not interact with light, that we don't see, and which is very important to understand why galaxies behave the way they do. And so I think this is certainly a very important issue, and It reminds a little bit what happened at the end of the 19th century, just before quantum physics and relativity started. People were talking about the ether, which was a kind of mysterious medium which was supposed to, through which light was supposed to travel. And then when quantum physics and relativity came to be understood, the ether disappeared. So what will happen with dark energy and dark matter? Will we find it, or will it disappear suddenly as a kind of myth that we have to forget? And I think what I would like to understand this problem, because I think it's the deepest problem we have now. The fact that we don't understand, we don't know what most of the universe is made of. And I think if this is a question, it is the most basic question we have to answer.
Professor Ketterle, you wanted to add something?
Yeah, I would say if I look at the evolution of atomic physics, for me it's an exploration of the big, vast Hilbert space. And we have only conquered or explored a small fraction of it. And by controlling single atoms, single photons, we are now trying with this control to put many atoms together into new corners of Hilbert space. And one corner is quantum simulation, another corner is quantum computation. But I'm also taking the approach that we have all sort of our goals where we would like to go. And there are new materials proposed here at the conference, and people work hard in the laboratory to go there. But I take sometimes the modest approach that we have this vast Hilbert space and many, many cool things are there to be done. But we are not really in full control because so many things we try just don't work because of available atoms, available lasers, available technology. Or maybe it's even that we simplify the problem to an extent that it doesn't reflect what happens in nature. So in that sense, I often feel we are not in control of nature. We are just constantly trying out where can we find places where nature allows us to play with her. And then we just go there and do cool things. But this is sort of what also the other people have said. We have our plans, we have our motivation, but when we go deeper and deeper in Hilbert space, we probably wind up in a different place. But it's good to have a goal.
One thing, because we have a general audience somehow, would any of you try to explain what a Hilbert space is to a normal audience?
Hilbert space is the space of all possibilities.
Oh. Very poetic. Actually, no, we wanted to, as we have, I think, some time, we wanted to maybe take a couple of questions from the audience, okay? So this is, I mean, we have the opportunity here, and as we actually invited a lot of people from everywhere, we would like to really take maybe 2 or 3 questions.
And maybe from young people, is there any young, maybe future researcher that is interested in asking a curiosity or something to our Nobel panel? Don't be shy. So. Perfect.
Somewhere.
Hello.
You have a badge from the conference.
So, Professor Ketterle, you said that you don't have any problems with quantum mechanics. You said that maybe you have some problem with the wave function of the universe because there is no observer. But then, wouldn't you like, don't you think that the need of an observer is just, in the quest of understanding the nature, is just a medieval? I would not like to run until the edge of the universe to face the problem. So wouldn't you like a universe that is independent of the scientists or the godlike scientists making the collapse of the wave function? Don't you think it's important to get rid of that?
If I understand you correctly, you feel uneasy about the scientists, and I don't think we need the scientists. When we teach quantum mechanics with the measurement problem or the collapse of the wave function, which Professor Cohen-Tannoudji described, and the observer, this is an idealization. But we know from many experiments, especially done by Serge Haroche, by showing the transition from the quantum world to a more classical world, that there is what we call decoherence, that the system is gradually losing its quantumness and becoming more a statistical mixture. And sort of this transition between how a measurement happens, at least some of it has been theoretically described and also experimentally demonstrated. So I think that, yeah, I don't know if I understood your question. Yeah, I don't have to go to the edge of the universe to maybe look at some of those issues. They are currently explored, but I don't see a real mystery. For me, everything I learned about decoherence, about the quantum measurement process, preferred pointer basis, all that has sort of helped me to even have more intuition for the mystery of the quantum measurement process.
Any other question?
Please remember that you can ask, I mean, let's say, how their career were or things like that.
Yeah, also the personal...
Oh, there is someone there.
My question is very simple. I just want to know which postulates you dislike the most. You know, there's many 7 or 8 postulates in quantum mechanics.
Maybe Cohen-Tannoudji can ask. Is there any postulate you don't like?
I think the postulate description of the state of the atom by a state vector and Schrödinger equation. And I think the postulate for the reduction of the wave packet is less important because it's still mysterious. It's not compatible, but it's strange because it's not the same nature as a postulate concerning the evolution in time. And I am sure there is something to understand there. And I think that is connected with the connection between classical world and quantum world. We have to be a little more clear about that border. Because, you know, we could try to increase the size of the system and to see, you know, of course, the Schrödinger cat is well known. It's a cat which is in a superposition of living and dead. That looks impossible to achieve. But atom can be in superposition of 2 states. You can try to increase the size of the atom, take molecules, big polymers, and try to find at what stage you can continue to get this superposition state. Of course, then you have the coupling with the environment and what is called decoherence. One of the big problems of quantum mechanics now is to have a full understanding of decoherence and try to how to solve, to fight it, to suppress it. That's not obvious. And I think in this direction, there are new things to do.
Thank you.
say
I
something
think there is
about-
another question.
Maybe I can add something about
Sure.
postulate, because when I learned physics, yes, I spent a lot of time, what are the postulates of special relativity, and then you derive something. And the postulate is, for instance, that the velocity of light is constant. In quantum mechanics, we also make those postulates. But I have to say, as a working scientist, I don't care so much anymore about postulates than to having a comprehensive working description of physical phenomena. And I think this is how people understood physics and how people developed the theory. It's more an afterthought when you want to write a textbook or describe or teach physics that you say, these are the postulates and this is what is derived from it. But you can sometimes turn things around and use this as a postulate and derive other things about it. So I would sometimes distract from the concept of postulates and say, in the end, what we have is a description of the real world, which is tested with very high precision and which works in so many situations.
But Wolfgang, you use Schrödinger equation to explain your experiment.
I know, but I'm aware that there are so many different formulations of quantum mechanics.
Yes,
and for me, it's not a single postulate, it's the full description, the full body of quantum mechanics, which we feel we understand or we have some uneasiness, but I would not single out single.
But I don't speak postulate, I think the behavior, there's a behavior, difference of behavior in the evolution of the spin 1/2 undergoing magnetic resonance, for example, perfect Rabi oscillation. And when you make a measurement, you find the atom here or here.
Yeah, okay.
So that's...
I think there is a big difference between the postulates of relativity, for instance, and the one of quantum physics. Because relativity, the postulates is just based on fundamental symmetries. So you have to accept that there is a symmetry in nature, the fact that you cannot distinguish the physics which is taking place in a frame that you consider being at rest or in a frame which is moving at constant velocity. This is an idea which came back from the 17th century, Galileo idea about relativity of motion. So this is a basic principle that everybody can agree with. Whereas in quantum physics, the postulates are based on more complicated issues, not only symmetries, but ideas which have been forced upon us by nature, by the observation of intricate phenomena at the atomic scale. And what I found already during my whole career, I have maybe one of the most amazing things I have found about quantum physics is the fact that these people back in the 1920s were able to find these rules while they were not able to do the experiments that we are doing now. So the fact that they were, even if they did not like these ideas, Schrödinger and Einstein hated the postulates of quantum physics, but they were forced to accept them because they use rational thinking by the observation of natural phenomena. And the fact that they were right, in spite of the fact that they did not like it, they were right, and that we have, now that we can do all these very sophisticated experiments, every day we confirm the fact that the nature works the way they said. This, I think, is a fantastic thing, and that says a lot about the power of human mind, and I think. And I don't know if human mind works according to the laws of quantum physics, I doubt it. But what is fantastic is that human mind was able to find these laws, and they are so powerful and give us so much power over the universe.
Okay, thank you. I think there is a question up there, yeah?
In the second floor.
Yeah.
Might it be that the observer observing the particle, when it's supposed to be there, affect on the particle being there? When there's an atom that has 50% chance of being on one side or the other, if the observer is observing one side, might it be that it influences it to be on that side?
Well, if the observer only looks on one side, he for sure will never see it on the other. So, on the other hand, we can be pretty sure that if there's a 50% chance that it will be on one side or the other, then the observer that is only looking at the one side will see it 50% of the time. We often say in quantum mechanics that the observer affects the results. And sometimes that can be a little bit misleading. When you make an observation, then the quantum system is in some new state as a result of having made that observation, and things progress from there. So in that sense, yes, the observation affects the result, and we talk about quantum back action and the way in which things are affected. But again, it's something that we understand really, really well. You know, some people have predicted that there's something else to quantum mechanics. We've alluded to it a little bit, that maybe when the quantum system gets big enough, that something else that isn't part of our understanding of our present day understanding of quantum mechanics, something else will happen when the system gets big enough. These are people who are uncomfortable with the idea that quantum mechanics should describe not only the microscopic world, but the macroscopic world as well. And somehow it seems that quantum mechanics doesn't really apply in the macroscopic world because of things like decoherence. Yeah, well, right. We have a few macroscopic examples, like superconductivity. But there's this feeling that some people have that once the quantum system gets big enough, that something else will happen, that it will automatically decohere even though we have sufficiently isolated it from the environment. There are no experiments that demand that kind of a result from quantum mechanics, and yet a lot of people would like to see that. And people are doing experiments to try to find out whether if they make a quantum system big enough, whether that will happen. Making a quantum computer will go a long way to either putting aside that idea or perhaps revealing that that idea is true. And that's one of the reasons why I'm enthusiastic about quantum computers. The thing I like about those kinds of theories are they predict something that you could measure. Whereas a lot of theories about quantum mechanics, or a lot of interpretations about quantum mechanics, predict exactly what the ordinary quantum mechanics predicts, and therefore they're not nearly as interesting because I can't test them. But these ideas are testable, and it's one of the things that we're moving toward, is being able to test some of these crazier theories about quantum mechanics.
You have time for one more question?
Everyone.
Yes, here there is one.
No, this guy.
Okay, thank you. You talked about the importance of building intuition. So my question is, how do you do that? What would you recommend us or our students? How to build intuition in a world which seems to be highly unintuitive?
Anybody?
Well,
Each of you.
answer is, I think intuition comes from deeply understanding selected problems. And if you have simple problems you deeply understand, then you can somehow apply the knowledge of simple systems to more complicated systems. Physicists who have great intuition are people who look at an equation and they know the solution without solving it, because they have seen solutions in very simple systems, and the features of the quantum mechanical solution now apply to more complicated systems. So that's my one part of the answer: deeply understand simple systems, but a deep understanding also requires to understand the systems from different perspectives. I often teach atomic physics in semi-classical or even classical approximation because I want to give students a classical, semi-classical, and fully quantum mechanical angle. And often when students get confused about quantum mechanics, I say, what would the problem be semi-classical? Then they get the right answer. So it's much easier to make a fool out of yourself if you only think quantum mechanically. So deep intuition requires this complete understanding from different angles, from different pictures.
Please.
So I agree very much with that. And if you're not as smart as Wolfgang, so that you can't expect to develop this deep understanding, then the second best thing is to have a teacher who does. And I have felt that a great deal of my physical intuition has come because I've listened to people like Claude Cohen-Tannoudji, Dan Kleppner, Jean Dalibard, and understood the way they think about quantum mechanical problems. And that way they think is very much like what you've said, thinking about things semi-classically, insisting on a kind of a physical model for what is happening. And this really helps develop intuition. So read Claude's books.
Okay. Maybe we can take a last question. There was one question here.
Professor Ketterle, $1 million question. In your intervention, you said that you had an understanding about quantum mechanics. In the 2 minutes and 30 seconds we have, could you enlighten us on that topic?
This is too much.
I think the question is about
quantum mechanics.
Yeah, to understand quantum mechanics. Maybe I would say, and this is why I made my statement, that most people who feel uneasy about the interpretation about quantum mechanics, and are now siding with Bill, feel uneasy about things which cannot be tested. Yes. And if something is not testable because it's more in the realm of interpretation, then I say this is not physics, this is philosophy. And I understand the physics. I don't say I understand all the philosophy and the philosophical implications, but maybe I'm happy to just ask physics questions and accept that for philosophical questions there is no answer.
Please.
I think that what Wolfgang is saying is quite in agreement with what Niels Bohr was saying, the fact that when you look at a physical problem, you have to imagine the experiment which will allow you to find the result. And so you cannot describe physics without having a complete description of all the apparatus which will be used for the experiment. Unfortunately, Bohr expressed this in a very obscure way. And so it was not very, he was right, but the way he was describing things was very often complicated and confused. And he even said it himself. He said that if you think that quantum physics is simple, it means that you have not understood it.
Yes. Well, but I think actually we are running out of time.
Yes.
So we will have to close this session. To close, we would really like to thank our panel for agreeing to be here. So thank you very much.
Thank you very much. And also, we would like to thank all of you for being here, enjoying physics with us. So, good evening, and see you next time.
Thank you. Yeah.